Hello, everyone, and nice to meet you. My name is Markus Konkol. I'm the Open Science Officer at the Faculty for Geoinformation Science and Earth Observation at the University of Twente in the Netherlands. And now I'm very happy to moderate a session on open knowledge, implications for the GEO work program. I don't want to waste too much time with small talk, since we are looking forward to a very, very attractive program that we can see on the next slide. We have a rich agenda that consists 6 speakers who will give brief 10-minute presentations. So I kindly ask the speaker to stick to the time, and at the end, we will hopefully have some space for a nice discussion and also for questions from the audience. And the focus of this session is to get insights into how the speakers have embraced open knowledge principles using the GEO Knowledge Hub, including its benefits and challenges. But let's first take a step back and take a closer look at the term open knowledge. It is not just a random term that was defined in the defined in the GEO statement on open knowledge. So the development of the statement was a collaborative effort, and I received a lot of support from people listed on the right. The statement was also greatly inspired by the UNESCO recommendation on open science and comprised several open practices, such as open reproducible research, open infrastructure, and open education. It is important to note that this statement goes beyond the most common open practices, such as open access and open data. So usually when we speak about open research, open science, the first things that come into our minds are open access to scientific publications, then maybe a bit of open data, but then usually it stops already. So rarely people speak about open code, open software, and so on. Also, the statement does not only consider technical aspects such as data, code, reproducibility, software, and so on, but also societal issues such as citizen and participatory science and the open engagement of people. Finally, the statement also aims to shift the focus from the scientific article as the only important research output as we experience it so far, to the other materials that are also essential. So we should focus a bit more also on the other materials such as code and data. This statement on open knowledge is not just a document that was approved without any follow-ups. So the GEO Knowledge Hub is already a concrete implementation of the statement. And as you will see today, it's also already operational. And the speakers of this session are already practitioners and use the GEO Knowledge Hub for the work, and thus also adapted open knowledge as defined in the statement. Next slide, please. GEO Knowledge Hub pays particular attention to open scientific knowledge, including not only the scientific article, but also the research data, the source code, and the software. And the contributions today will show that the scientific article is not the only important research output. Just as important are research data and the methodology in the form of source code and software. And the GEO Knowledge Hub is operational and ready for exploration and contribution. So you can follow the link, check it out, and also provide feedback if you like. For more specific information, I kindly ask to contact the GEO Secretary. Now the next slide, please. However, we are just at the beginning. So we have an open knowledge statement, which was approved already. We have the GEO Knowledge Hub, and we have a couple of contributions that we will hear about today, provided by our speakers. The idea now is to learn from these contributions and extract some best practices. In addition to these best practices, we would like to establish some open knowledge guidelines. And the result will be some sort of a white paper, or maybe also a living document that helps those who would like to use the Knowledge Hub. So it would be nice if we can also use this session as some sort of a kickoff for the development of these guidelines and best practices. Next slide, please. And for that reason, I kindly ask everyone to keep in mind while listening to the presentations and maybe to contribute with ideas and suggestions. And to make the whole process a bit easier, we have a few things to consider. So please change, first of all, your name into organization and full name, as shown on the slide. Please mute your audio when you don't speak. If you have questions or comments, you can either raise your hand, which is the recommended option, or request the floor in the chat. The moderator, which will be me, will give you the floor and allow you to ask the question verbally. You can also comment, so you can make comments in the chat without requesting the floor. And we will also take the opportunity to start a poll here and there after some of the presentations. Be aware that this meeting will be recorded, and in case you are using Twitter, don't hesitate to follow GeoSec 2025, and please use the hashtag EO4Impact if you are tweeting. So now it's my pleasure to introduce the first speaker, which is Brian Killough, who has quite a bit of NASA experience and leads the Committee on Earth Observing Satellites. He has played a significant role in the evolution of the Open Data Cube initiative and has authored over 20 technical papers. Moreover, he received the NASA Exceptional Service Medal in 2016 and the 2021 GEO Individual Excellence Award. Brian, the floor is yours. Thanks for coming.
Thank you. Appreciate that intro. So good morning, good afternoon, everybody. I'm your first presentation of the day. So look forward to telling you about the Open Data Cube Sandbox. This is a contribution to the Open Earth Alliance. So next chart, please. So a little bit about a data cube. Some of you may not know what it is. This language has been used quite a bit around CEOS community and around GEO community. So if you think about satellite data in terms of its dimensions, if I look at things spatially and I consider something like latitude and longitude, and I stack that data over time as I gather that data and go around the world, I can stack that up in what we would think about as a cube. It has the dimensions of latitude, longitude, has the dimensions of time. And then the smallest measurement we have inside of that cube are things called pixels. And in the case of something like Landsat, those pixels are perhaps on a scale of about 30 meters. And if you look at this example on the bottom, it's about the size of a baseball field, the inside of a baseball field. So that gives us an idea of what we're looking at when we're looking at these data cubes. Next chart. So we came up with this concept within the CEOS organization of something called the Open Data Cube. And what this is a connector in between the satellite data and how we work with that data through applications. If you don't have anything like this, there are certainly ways to analyze the data. It just becomes a little bit more difficult and harder. And so by forming this geospatial management structure in between, we have some core code and some utilities and an API that allows us to access that data more efficiently and quicker and faster, and to kind of simplify how we do our coding to get quicker to the applications and the final products. So that's what the Open Data Cube project was all about. Next. So what has spun off of that is something called the Open Data Cube Sandbox. And this is what I would say is our primary contribution to the GEO Knowledge Hub. So we put together this idea and we linked it to Google Colab. So the tool we have is completely free and open. It runs on a Jupyter Notebook interface, and it's all linked to the Google Earth Engine data sets. So it's a little different than Google Earth Engine directly, and I'll tell you the differences in a moment. And what we've done is allow people to go to this sandbox and run applications that are pre-canned, where we've developed some algorithms that can run these apps anywhere in the world. So we can look at things like cloud statistics from Sentinel-2 or Landsat, spectral products. We've got things with filtering of clouds to create mosaics, vegetation extent. We've got a flooding application for radar, VIIRS night lights. We have some ALOS radar land change data, digital elevation, land cover. We're now up to 19 different applications in this sandbox. So a lot of really interesting ways for you to look at this data in a free and open way, to take a look at the code that's behind it, and to see how does somebody interact with this data and utilize it. So it's really an ideal tool for open science. It's generated a ton of interest in both the research community, and I would say even more so as an educational tool. If someone wants to learn a little bit about Python coding, if they want to learn what are the methods to interact with satellite data and not be so intimidated with it, jumping right in, this sandbox is an ideal way to do that. Next chart, please. So what are some of these benefits? As I said, we're using the Google resources. So that means everything we're using is free and open. We're using their data, so all the satellite data from Earth Engine. we're using a Colab Jupyter Notebook server. So that is their server that allows us to code, and it's basically a platform for coding. It's called Colab. And then we're using the Earth Engine framework for the computing. So you don't have to go out and purchase a computer. You're using the same framework that they use for the Earth Engine. The difference here, so it uses a lot of free and open source software. So all the Open Data Cube stuff is open source. And we have a library of common GIS functions. So if you were to compare this to what you would do in Google Earth Engine, these common GIS functions are not necessarily all available. So within the Open Data Cube community, we knew that most people want to use this data for certain purposes, the kind of things that we tend to do frequently. So we canned a lot of those GIS functions, making it a little bit easier to use in Google Earth Engine directly. And if you're going to Google Earth Engine, you either have to use the Python API or a JavaScript interface. And in many cases, unless you're a coder and already have an application ready to go, you start with a blank slate. And in our case, you don't start with a blank slate. You start with a number of currently running algorithms. So we've been growing our set of users, and then we have this library now of application algorithms. We have about 19 of them, all hosted in GitHub. So basically, when you go to our Open Data Cube, it's actually openearthalliance.org/sandbox will get you there. And when you go there, you'll see it links you to a GitHub. And on that GitHub, you will find these 19 posted Python algorithms. Click on any one of those, it opens it up, and it actually allows you to start to run it with a series of steps. It's really easy to start, and it's easy to share these notebooks, and you can share them via Google Drive or with GitHub. So one of the interesting things is you can take any one of these notebooks and you can modify it to your liking, change a few things, and then you can save it locally to your Google Drive and then share it with other people. So it really does promote an open science framework. Next. So just to give you a few bits of information about challenges, or let's just say some constraints here. There are limitations in how this runs. So the memory is limited to about 12 gigabytes of memory. Now, it might not mean anything to all of you, but let's just say it limits the size of your analysis. If you want to use this sandbox, which is free, and basically it's operating on Google's framework, you're not going to be able to do an analysis of an entire country or some massive amount of time. So there's some limitations there. But you can do decent sized things. You can do, 1 degree square, a couple years worth of data, and it might take a little bit to run. Some things run in a matter of minutes. Other things may take, quite a few minutes to run. Just kind of depends how you set it up. And then there's some storage limitations, 100 gigabytes for output type products. Once you open those notebooks and operate on them, you're limited to 12 hours of operation. But all that means is that you could log out and then log back in and start a new session. So the other thing is that Python is not commonly used by everyone, but it is becoming quite rapidly the choice for most GIS developers. So if you don't know Python, that's okay. There are a few really simple algorithms that we have that get people started. I have taken this and I have shown this to high school students. I have shown this to non-GIS people, and a number of people from an educational perspective. They catch on pretty rapidly, and they're actually excited by the thought that, boy, I might be able to code a little bit and learn about how this stuff works in the background. So all you need is two things. You need a Google account. So if you've got Gmail, you've already got a Google account. And then you get this Google Earth Engine authorization, which is actually a pretty simple process. It might take a matter of minutes. Sometimes it might take a few hours, but that's pretty easy as well. Next chart. So here's an example. One of the outputs from our flooding product, and this is a SentinelOne flooding product. So what you see is the plot on the left is actually the water extent over this area in Guatemala called Campor, Guatemala. There were 2 tropical storms that hit this area. Tropical storm Eta came in early November, and then Iota in late November. And what you see is the increase in the water extent over time for this little small town. This town was severely flooded, and on the right is a time series animation. All the products you're seeing right here on the screen are all available through one of the notebooks that we have posted, which is our Sentinel-1 flooding notebook. There's been a lot of interest from this notebook from the International Disasters Charter, because this would give people the capability to use something like this for after the initial peak of the storm, which is when most people are most interested, right? They go out and they make do analyses for the storm inundation, but the recovery period that follows is also of high interest. And being able to continue to track this over time is valuable. Next. Here's another example for a land cover data product. We've looked at several of these. So we have some notebooks that look at the ESA world cover, which is a 10-meter resolution. This is Kumasi, Ghana. And the one on the left is 10-meter resolution. You can see the detail. The one in the middle is the 100-meter resolution Copernicus land cover product. And on the right is a 500-meter MODIS product. So just by taking a quick look at this, you can kind of see the granularity and the detail that you might get if you wanted to use a 10-meter, 100 or 500-meter product. There's quite a bit of difference between them in terms of details on what you can see. Next chart. So how does all this relate to the Open Knowledge Hub? We see this sandbox as a contribution to the Open Earth Alliance. And when we put together this community activity for the Open Earth Alliance, it was all about promoting the use of open data and open technology solutions. Open Data Cube is one example of that. And over time, I suspect there'll be more of those. We certainly think it's an excellent example of open data and open science. It promotes data transparency. It has replicability. We can reproduce any analysis that you have running here. All you need to do is jump in, use the code, and rerun it again. And we've noticed that the sandbox has applied to a real diverse set of users. I would say the one that's gotten the most interest initially is our students, people that are brand new. I just had a set of students here locally at NASA that came through. I had several students that did not have any GIS background, and they jumped into this, and within 10 weeks' time, they were coding and really enjoyed it. Researchers and decision makers are ones kind of up the value chain that could use something like this. Next chart. So what's coming in the future, and where do we see this going? Right now, we have this running on Google and the Google platform. We're looking at taking the same exact concept and running it through Amazon, Microsoft, and the Sentinel Hub, using all of their free resources as well. And what we found is that Amazon and Microsoft also have very similar coding type platforms with some free compute in the background. And we think that we can set up something similar. So that way, if someone wants to go to any one of these platforms and experiment a little bit, they can do so. Now, remember earlier I said that you can only do small analyses. If you want to do a larger analysis, basically that means you would have to go purchase some larger framework, larger cloud environment. You can then take any one of these algorithms and scale them into that environment. Perfectly fine to do a larger analysis. We're seeing a big difference in data formats. So CEOS has been working this a lot. We're now using analysis-ready data for everything we do. Stack metadata is a way to describe the data that we're interacting with. By using something like Stack, it allows you to interact with that data even more efficiently than we have in the past.
Brian, 1 minute left.
All right. It's the last chart, so I'm right on. There's more regional and local data cubes around the world. We're seeing a lot of these pop up. There's been broad adoption by governments and academia and even industry. We're seeing industry take this concept because it's open source software and adapt it to their own problem and create a solution. Faster compute times and parallel processing. You all know what cloud computing is doing for us these days. It's only getting better. Python proficiency is rapidly growing. It seems to be the code of choice right now, and I'm seeing a lot more people learn it. We're building more application algorithms. We're using more data sets. And then finally, I'll mention some interesting things about the kind of data we're using, and that is drones and Internet of Things. We're starting to do some testing for implementing data from drones or Internet of Things into data cube frameworks so that you can use it simultaneously with satellite data. That should be a really interesting twist, and we're looking forward to that. That's it. I don't know if there's a last, there's the last chart. If you want any of those links, Open Data Cube Sandbox is at openearthalliance.org/sandbox. And thanks again.
Great. Thanks a lot, Brian. That was an excellent start into the session. For the newcomers, if you have any questions, please ask them in the chat, and we will come back to them after the talks. I would like to come to our next speaker, Robert Chen, who is the director of the Center for International Earth Science Information Network of the Climate School at the Columbia University in New York. He has managed the NASA Socioeconomic Data and Application Center for more than 25 years. Currently, he co-leads the GEO Human Planet Initiative. Robert Chen has also played a lead role in the GEO data sharing activities and co-chairs the thematic research network on data and statistics of the United Nations Sustainable Development Solutions Network. Robert Chen, I would like to hand over to you.
Great, thank you very much. Good to be here today. I'm representing the Human Planet Initiative. Actually, a couple of my co-leads on Human Planet are in the audience, but they're from the Joint Research Center of the European Community. So I appreciate their inputs. What I thought I'd talk about is really how open knowledge interacts when we think about the human planet, and it's really critical to engagement with stakeholders and to GEO's engagement priorities generally. So next, please. So in that context, I mean, I think this is something everyone understands, but it's important to always remember, you know, just how tightly coupled human and natural systems are. There's human systems cover a whole range of sectors. Obviously, natural systems, you know, we think of Earth systems as being very well, very tightly integrated, and there's lots of feedbacks and interactions between them. And so naturally, being able to take both human and environmental data and work with them in a very dynamic and integrated way is really important. About a year ago, the US National Academy of Sciences released a report kind of reiterating that. That's where that little diagram comes from. And so in the initiative, we've focused on, of course, on using Earth observations to improve just understanding where people live, their settlements, their infrastructure, and you know, the characteristics of the population. And we need to do that, you know, from the past to the present and into the future. And of course, what we find is that these have very many diverse applications. Next. So I know everyone's familiar with the Sustainable Development Goals, but I think this is another case where it's clear that most of the goals need to know where people live, who's affected, who can make decisions, and that these are very integrated. Next. So that's really, you need data. And I'm approaching this as sort of the continuum from the raw data that we collect to, you know, producing useful information, but then creating open knowledge that allows people to make decisions. So as we go from data, you need, of course, metadata or information, but also the outputs of models and predictions themselves are useful information for decision-making in any of the SDG areas or other forms of decision-making. Next. And so, you know, we get to this idea that we need open, shared, trustworthy knowledge about both the human and environmental aspects of our planet. Next. So just quickly, of course, I can't go through all the different kinds of data. I'm sure you've seen some of this. You know, a lot of Human Planet has focused on using Earth observations to identify built-up areas, both, you know, building footprints and that sort of thing, impervious surfaces and so forth. Next. And then that is a key input into thinking about settlement modeling, you know, what are urban rural distinctions, next, and how this informs what we understand about human activity on the planet and who's affected and is affecting the environment. Next. Oh, and yeah, next. So then as we move kind of into the information space, we need to look, for example, at future projections. Where are people going to live and what is the land use? And for example, urbanization is expressed here. Next. And another form of information is understanding all the different data, what their pros and cons are, what their limitations and uncertainties are. We developed a tool at my center, which just allows you to compare all the different gridded population data sets available and get a sense of the variation and how they differ at particular places around the world, because data, different kinds of methods and models work better in some places than in others. Next. But then as we get into the knowledge space, I think it's important to look at how the data and information is used in context and as part of the process by which science informs policy. So a good example, of course, is the Intergovernmental Panel on Climate Change, which I'm sure you've seen has released 3 different reports over the past few months. In the impacts report, for example, gridded data was combined with a whole set of data on mean and extremes of precipitation and so forth. And, those were data inputs to provide information that was then part of a kind of a knowledge package itself, the whole IPCC 6th assessment. But you can see examples of this all through that report. Next. Next. And of course, in the SDG process, next, there are many examples in which human planet data has been integrated into the various indicators that inform progress towards the Sustainable Development Goals, which of course the world hopes to reach by 2030. Next. So as we look at the Knowledge Hub, I think we're familiar with a lot of different challenges. We've tried to make human planet data open and reproducible and to give the tools as well as the products for people to recreate them. Next. For society, we need to better understand those processes and the interactions and being able to put them together in tools like the Earth Cube we heard about and through other means. Next. We do think that having the human part is really essential to addressing the challenges and the decisions that have to be made both at the local, from the local to the global scale. Next. And we're really interested in how to get better use cases and feedback from practitioners and policymakers and to make the data more useful and targeted. Next. So looking ahead, we are in the process of building out the knowledge packages we have in the Knowledge Hub. Each knowledge package is very context sensitive. Every sector, has somewhat different needs, and we've been trying to adapt to those. Obviously, we want to get our broader human planet community more directly working with the Knowledge Hub to kind of build their own resources and also the linkages between them. And I think that, one of the biggest challenges is how to integrate the kinds of tools and data and services that we provide with all the other initiatives and flagships that really, can use the best available information about where people live and how they're both affected by and affecting the environment. And I've been using this cartoon a lot. It's nice. We have to collaborate because, as we can tell, the disasters are coming faster and more together than we are. Next, I think that's it. Thank you.
Thank you very much. That was an interesting presentation. Once again, the note, so if you have any questions to the speakers, please ask them in the chat. We'll collect them and come back to them after the end of the talks. So we reached the impressive number of 94 participants in the session, which is great and gives us the nice opportunity to collect some input from you. So Florian Franciscakis prepared some poll questions, and we would like to start now with the first one. So Florian, could you please, there it is. So I kindly ask the audience to take a few seconds to answer this question. And we leave it open for 1 or 2 minutes. So yeah, then we will continue with the next speaker. Of course, we will show the results at the end. All right, so while you are maybe still typing, I will already introduce our next speaker, who is Monika Kuffer from ITC. She works on remote sensing, urban spatial analysis, sustainable development goals, urban equality, and urban environments. She co-chairs a network on deprivation area mapping and works on several research projects on urban deprivation and environment. Moreover, she is the project director of the NAFIC funded trainings, and she is also part of the steering committee of the joint urban remote sensing event and the chair of the developing countries and a member of the EO for Sustainable Cities and Communities Toolkit. So thanks, Monika, for coming. Yeah, the stage is yours.
Thanks, Markus. And it was a nice sequence, and particularly great to have my previous speaker setting really nicely the scenes of all the Earth observation data which are out there for SDG related, for development related questions. So I'm Monika Kuffer from ITC, same place as Markus, but in principle, I'm talking today as a representative of the EU SDG Toolkit group, where we particularly focus on the urban SDG and the new urban agenda, and looking into how we can opening this archive, massive archive of Earth observation data to make it useful for local level, meaning city level, national level, reporting of urban SDGs. Also, as we have been working already for, more than now 1 year as a group together, maybe also sharing some of the experiences which could maybe contribute also to the GEO Knowledge Hub development. If you click on the next slide, please. So that's basically where also one of our working groups is very active in seeing how our learning lessons on how making data available to local actors can be sort of contributing to the development of the GEO Knowledge Hub. In principle, let's say what the GEO Knowledge Hub does, it's an open library, and it includes information about methods and results. It documents, it puts data available, shareable. And I think a very important aspect, at least what we also learned from the EU SDG Toolkit group, is how to document data and how to make it available for necessarily not, also for non-urban, not Earth observation experts, but for people who want to use and take this data. Next, please. So what we do within the Earth Observation Toolkit for sustainable cities, communities, we have been creating a massive online knowledge resource that is providing in a very structured and documented way Earth observation data product that can be taken up by local users to support a local SDG reporting and further questions on the new urban agenda, environmental urban questions, etc. And we structure the data, and that's one of the important elements that we have been developing a very clear structure that helps end users to sort of organize and get access to the data. So we use, for example, categories like typical categories like urban scientists are working on housing topics, on open space, urbanization, information related to public transport. And an important element, so it has been guided by UN Habitat as putting also the whole frame of the urban SDGs, and with a large group of international experts, which is a mix of Earth observation experts, but also city level users, and particularly this end user perspective is very important in the development of such a toolkit. Next, please. So what you see, and that's also a bit from my background, so we are looking now to a city which is Khartoum in Sudan, a city which is massively growing, and that's a typical example from a global south city. The urban growth is driven by, in this case, by migration, by displacement, by climate change, and data are typically missing. So data are either really dated, like in the case of Sudan, the last census dates back to 2008. Even this census is very, at least doesn't give a good picture. And in general, data are scattered, if at all available, they're very dated and don't provide really city level actors a good base to make decisions. And what you see on the right is an example on an SDG related aspect. So what we see is a nightlight image from the International Space Station. And in the lower part, you see this red area, which is one of the informal by displacement driven settlements. And you see that this area is pretty simply not connected with the city infrastructure. Seen by it's not connected with the electric grid. And that's some data which need to be processed and being put in the hand of local actors to base decision on urban development questions, for example. Next, please. So what is important in forming such a toolkit and make it usable and open up this massive amount of Earth observation data to a large amount of users and beyond our group, which are the Earth observation people, which are already even struggling with this massive amount of Earth observation data, like Bob was showing before, like the PopGrid viewer, which is documenting different population data. This is already confusing to us. For a local user, it's getting even more confusing because they need clear documentation, they need guidelines, they need easy to use data. And therefore we have been combining Earth observation experts with city level and government level representatives and developing also use cases for many locations to show the usage and the potential, but also the limitations of Earth observation based data for SDG related questions. Next. So what is the objective of the toolkit? So it's really opening up Earth observation data to a much broader user group and making access as simple as possible. We are still in this process of doing it, and we're having discussion on how to even better make data accessible. So what we start with is like an understanding of local information need, local monitoring need. You need to build, and that was also Bob was referring to before, we need to engage with local end users beyond our sort of group of Earth observation scientists, really understanding and also making this sort of connection and forming networks. We need to make data much more documented. When we look to our way of producing Earth observation data, they are there, they're open, but they're not accessible. People are not, methods are there and documented, but they are not replicable for local users. because they are not produced in a way that it's easy to be taken up. And we need to really support particularly the southern countries or the low and mid income countries in improving their capacities on accessing data, because they're typically the massive questions existing on massive transformation of the landscape, of urbanization processes, which are pretty much uncontrolled, and the massive destruction of natural spaces. And we want to become, as a toolkit community, really the point of, okay, if you look for data on urban related SDG and new urban agenda questions, that's the place you should go. Could you click next? And we have one group that really looks, and that's one of the important principles. So each data set, and I would like to ask you to visit the portal and look also, maybe you find also data sets which should be there, which are not there. So what happens with all data sets which are going into the toolkit, they are screened under the fair data principle before they are entering the toolkit. And they're also then getting into the documentation for users. Thanks, next. So what we also see important is to develop use cases that allow city level users to understand the potential of Earth observation data, and illustrating for, in this example, for different SDGs like inadequate housing or land consumption or air pollution, how Earth observation data step by step can be used to finally arrive with a local monitoring, maybe a local a report on this specific SDG building on Earth observation data sets. Next, please. So what we have been compiling so far in the toolkit are this four major elements. So we have very important guidance documents which are descriptive in a very easy language, which has been developed also together with local users, the data sets itself, which are structured and organized. The same for tools, also classifying the tools as more advanced tools or as compared to more easy use tools, and well-documented use cases, which should stimulate knowledge exchange and the uptake of Earth observation data by users. Next, please. So data examples in the use kit or in the toolkit are, for example, the global human settlement layer, which is a very long time, have a very long time history starting from the 70s, which shows the presence of human settlements. If you click on the next slide, I hope the animation runs if you click on it on the screen.
Monika, 2 minutes?
Yes. Yes.
Thanks.
So what you see is the tools, the data are structured according to the SDGs. And if you click on one SDG, like the one on land consumption, you see the related data sets like the build-up map and the related population data sets, which you would need for reporting on this SDG. Or other SDGs like air pollution, where you see then the layers that allow you to map air pollution aspects, air quality aspects, or before what I showed, the nightlight aspects, which are relating to the SDG 11, which can be extracted and displayed for SDG reporting. If you go to the next slide, please. So we hope that also the way and that we can stimulate with the GEO Knowledge Hub. Also, I think many examples which we have been developing, but also which already there can maybe flow into the toolkit. So I think there's a lot of cross stimulation, possibly exchange of information. Next, please. An important aspect was also the documentation of all the tools and having a very simple documentation in form of one-pagers. For each SDG, there's a one-page documentation of the data and what can you do with this data for this specific SDG monitoring, which are written in a relatively simple language, but also happy if there's some review on that and feedback. Next, please. And a final aspect, also what we want to still further develop, is the use and the sort of linkage between Earth observation data and community-based data. As we see, there's a huge potential if you combine this in understanding aspects of the urban environment, aspects of living quality, deprivation, contamination, like shown in this example of an ongoing project in Kenya, where we combine Earth observation data with community-based knowledge to characterize urban environments. Next, please. So if you are interested in it, please get in contact us, join us. There's a huge group and some people are visible there. So it's a very nice active group of people really putting together Earth observation related information on urban topics and really making this information more accessible to a larger community. And if you click next, then you will see some contact and also particular contact of Archie, who is coordinating this whole effort. I think she's also with us in the room. So please get in contact with us and please contribute. Thanks, Markus, over to you.
Thank you very much, Monika, for this nice example from my home institute, ITC. Thanks a lot. So if you have any questions, don't hesitate to put them in the chat. We will come back later. We will go on with the next speaker, who has the very nice name, Francesco d'Amore. He is a data and software engineer and researcher from the Institute of Atmospheric Pollution Research. He likes designing software architecture and is interested in new approaches to data science. His experience is very diverse, including different application scenarios such as finance, environment, and GIS. Currently, his main tasks are the management of environmental data and the design of data processing. Francesco, we are looking forward to your presentation.
Okay. Thank you. The next slide. You can hear me? Yeah, okay.
I can hear you, yes.
Okay, thank you. Just an idea about our project. Ghost4M is a project aimed to support effectiveness of evaluation of the Minamata Convention on Mercury. So the goal of our project is to collect data about mercury pollution coming from different data sources around the world. And the next slide. Using this data, we define a digital architecture, a cyber infrastructure. That is the target of this digital infrastructure is to share our data, our knowledge about the people interested in our topic. For example, researchers, but also stakeholders and public decisors on the topic. In order to define this digital architecture, we compose together the different tools in order to define a more robust technological stack, and this technological stack can share with our users our knowledge, our data, and so on. The next slide. In this slide, there are some idea about our architecture, our services. For example, we manage more than 100 dataset and services, federated network for the topic, but also we are working on federate more network on mercury pollution monitoring. And by means of that, we want to collect metadata about this network. For us, metadata are very important because we federate this network by means of metadata. At this end, we have a metadata editor, in this case, a customization of the network open source, and we define also a thesaurus on the topic, on mercury pollution, in order to be the metadata more effective on our topic. In order to share the knowledge about our topic, in order to share the data sets and the information and the services, we use different knowledge hubs, not only one. And in the other slide, the next slide, please, we give an idea about all the different knowledge hubs that we defined can work together in order to share the knowledge about our topic. In this slide, we have a very quick picture about our network, about our cyber infrastructure. We collect together data and the metadata in our data catalog, in this case, GEO Network. And we collect not only metadata, but also data using a server map. And this collection of information is very robust because we are using different OGC standards. So by using the standards, it's also possible to link in a very easy way the data that we collect will more complex more complex federated system. In this case, by using GeoDub, it's possible to harvest the information and collect this information in the GEOS platform, in the GEOS web portal. By means of the GEO network, by means of our data catalog, we federate together the information on different knowledge hubs. For example, we defined inside knowledge hub developed inside our framework, we collected information of this knowledge hub and we carried out this information also in the GEOS platform. Also, we put some knowledge, some package in the GEO Knowledge Hub provided by the GEO community, and we use a different knowledge hub in different way by match the different requirements of our users. In the next slide, here we have some idea about our metadata editor, because in our architecture, the GeoNetwork data catalog is a crucial point, and this is the central point, because we use GeoNetwork in order to collect data, but also in order to link this information in the GEOS portal, of course, but also in the GEO Knowledge Hub. Next slide. For example, here we have an idea about the GEO Community Portal. By means of the GEO Community Portal, this is a community portal focused of our project, Ghost4M, but also we connect the data in the main GEOS web portal. And by means of that, our dataset, our services, not only dataset, but also services are discoverable and searchable for people interested on. By means of that, it's possible to search about our dataset. It's possible to download data for people interested on the dataset. This is a very, in my idea, a very effective way to share our information with the community, with the search, with the research, and so on. But also in the next slide, okay, here we developed some, let me say, knowledge hub defined in order to share in a very complex way the knowledge about our topic, because by means of the GEOS portal, it's possible to download the data per se, but by means of this type of tool, it's possible to use our data, the data that we collect, in order to provide our knowledge about the topic with more high-level users, not only researchers. For example, this type of tool is used by policymakers, stakeholders, in order to simulate different scenarios about mercury pollution and to compare the different scenarios at the global scale in order to take the better decision based on our data that we collect around the world. So it's a web dashboard composed by different widgets, and by means of that, it's possible to define the scenario about mercury pollution and mercury emission reduction around the world, and it's possible to provide this type of scenario to stakeholders, policy makers, public decisors, and so on. But in the next slide, okay, here we have the GEO Knowledge Hub provided by the GEO community, oriented, there is a searching for our project, and here we put all the knowledge package related to our project. The two knowledge hubs are different because serve different type of users. In the first case, the knowledge hub developed inside our project, we serve, for example, the Minamata Convention and the target of Minamata Convention. So policymakers and stakeholders have to take decisions on the topic. And there are some simulation about the mercury reduction and mercury pollution. Here, this type of knowledge hub is used to discover the information. So there are the different scope of the different knowledge hub. In the next slide, we provide a comparison between the different knowledge hub that we use in our framework, because our idea is that there are not a single killer application that can serve any type of users. So we define in our technological stack different application, different knowledge hub in order to search different type of users. For example, in my opinion, also the data catalog is a knowledge hub. So For example, here, the GEO network is possible to define also the GEO network data catalog as a knowledge hub, but it's used mainly for researchers that want to download the data per se. In other situation, for example, the knowledge hub, the GOS4M knowledge hub is used for policymakers that want to use not the data set per se, but I want to use the data set with a post-processing. You want to provide more high-level information in order to take information, in order to take decision at different levels. And the other knowledge hub, the GEO knowledge hub, is used for by general public. They want to discover the component of our architecture. So each type of application is used for different requirements, different type of users. And or at least it's different type of user of our project. In other type of scenario can be used also in a different way. In the next slide, there is some open issues and of our infrastructure. For example, at the moment we provide our information with an open access approach, of course, but we have some problem using looking for data licenses that can match the requirement for our data and our processes. Metadata, for example, for us is a very important thing in order to share the knowledge, but to maintain the metadata is a very important effort that we have some trouble about that. And okay, just this. There are many issues, and we have to, in the next feature, we want to fix this type of problem. Thank you, Markus.
Thank you very much, Francesco. It was very interesting to see your lessons learned and also the open issues. Our next speaker is Riley Hales, and for some technical reasons, I kindly ask you, Riley, to share your screen. In the meantime, I will already introduce you. So Riley Hales is a hydraulics and hydrology researcher, which has been part of the GEOGLOWS streamflow modeling project. He contributed to the development of the streamflow hydrological model and designed the web services and apps which make this project unique in the hydrology world. He is experienced in numerical water modeling, statistical analysis, machine learning, web technologies, and decision support systems. He has been involved in projects to increase the capacity of hydrometeorological agencies in more than a dozen countries. Currently, he is doing his PhD in civil engineering at Brigham Young University. Riley, the stage is yours. Thanks for coming.
Yes, thank you very much. So as was mentioned, I'm part of the GEOGLOWS project, and I work specifically on a global hydrologic model, which we call the GEOGLOWS ECMWF streamflow model. The outline of my presentation today is I'll briefly explain what that is, the kind of the unique approach that we took to hydrologic modeling there, and how that ties into the GEO work program, the GEO Knowledge Hub initiatives, some success stories of how that was used and what we learned through those case studies. So the GEOGLOWS ECMWF streamflow model is a global hydrologic model, as I was saying. We provide discharge simulations around the world. Our model has about a million reporting points and has the coverage you can see on this map. We provide principally two data products, a historical simulation of streamflow and an ensemble forecast, which is produced every day at midnight. And that covers 15 days at a time. These data sets have been used for a wide variety of applications, which I'll briefly mention later in the presentation. But I'd like to also take the chance to, while I'm here, recognize all the logos on the bottom right. This is not just a GEO program. This was contributed to also by ECMWF, Aquaveo, NASA, the World Bank. More people than honestly I could put on one slide here. But diving a little bit into the model, you might say that a hydrologic model has these components that I've listed here. And starting on the left, as a scientist and a researcher myself, we're prone to spend a lot of time on these things I've highlighted, like the choice of data sets, the choice of numerical modeling algorithms, the choice of which cloud provider am I going to use to execute all of this, how am I going to perform data assimilation, all these really technical things that I'll label as of interest to the model builders. But where GEOGLOWS has taken a unique approach is they've pulled the scientists and academics like myself out of the strictly the purely technical aspects, and we spent a lot of time building these companion services. We're often interested in end users, what kinds of data services would most support a local user, what kind of graphical interfaces, visualization services, web apps, training videos, etc., would be useful to an end user, so that we're not just a hydrologic model, but we're something that supports end users at a local level, builds local capacity. Specifically, we've built a variety of web apps and a whole training websites, which we often refer to as the GEOGLOWS toolbox. And as I was just saying, we had this as on our own website for a long time. And just recently with the GEO Knowledge Hub initiative and really any initiative that supports this open knowledge concepts, transparency in model making decisions, accessibility to data sets, that's something GEOGLOWS has been interested in for many years, and we're very grateful to see the broader GEO Work program also contributing to these kinds of approaches, the open knowledge approaches. So I'd like to quickly share a handful of ways that our global hydrologic model was used, and then we'll wrap up with some reflections on what we learned through those different case studies. These success stories cover everything from flooding to water quality to early warning systems, as well as some bias correction, more technical things. So first, in late 2020, there were 2 hurricanes that came through Central America, and we worked with some reservoir operators at El Cajon Dam in Honduras. After the first hurricane came through, it significantly raised the water level in the reservoir and disabled a lot of the gauges on rivers that are upstream. So when the second hurricane was forecasted to hit, the reservoir operators were sort of left blinds, didn't have the local capacity to do their own local forecasting of what's going to happen to the reservoir. This brought up a lot of concerns on, excuse me, or is the dam going to overtop? Are the people living downstream of the dam in danger? Are we going to lose lives or property? And so they used the GEOGLOWS data services, the Python packages, all the web apps that we've developed to inform their decision making. We produced some graphs like this after the facts, and you don't have to spend too much time looking at all the specific numbers, but the red line shows what's they observed as the inflow to the reservoir, and the blue center line, the solid line in the middle, is the average of our forecast. And this is for non-hydrologists, suffice it to say that it performed quite well, and the reservoir operators had a reliable source of data, were able to make wise decisions to inform their releases and prevent any of those possible catastrophes. The next example is just to the west of Honduras in Guatemala. This is Lake Atitlan shown on the left. This is a lake known for beauty and clarity of the water. It brings in lots of tourism, but it started to experience seasonal algal blooms, and they had concerns about water quality. So the local water managers and the people living around the lake wanted to do something about it, but neither they nor at the national level were able to come up with the hydrologic study of the surrounding areas, as the rivers that feed the lake contribute to the nutrients and contaminants that could cause the algal blooms. So they similarly were able to, in lacking local capacity, drew on global sources of data using the Python packages we developed, the web apps and the data services, and that spurred on a environmental analysis that otherwise would have, if not been impossible, it's just been very costly and time consuming and prevented real work on the problem. The next, in Nepal and Malawi, There have been other places, but I'll share just two. In Nepal and Malawi, they've used our hydrologic forecast to complement flood early warning systems. This picture I'm showing is a river in Nepal, and a local school teacher that lives nearby this river knew that the river was prone to flooding. Flooding season was approaching, and he came in contact with our global hydrologic services. And on his own, without help from local governments, at least initially, saw, hey, there's a flood coming, and informs the people around there. This is picture showing crews going to clear out debris and things to prevent damage and to property and loss of life when the flood came. They also took that one step further and created a customized web app that implements our same data sources, built on the Python packages and modeled after the web apps that we've built to create their own flood early warning system, essentially. And similar story goes in Malawi. They have a community-based flood early warning system, which has very limited forecasting capabilities. So they took our global data sets and were able to extend how long their flood early warning system provides for lead time. And last quick success story is supporting more of at an institutional level, the Hydromet service in Nepal. They're a classic example of someone that desperately needs more hydrologic capacity, and excuse me. So they really need this kind of local capacity, but have very limited observation capacity to do it themselves. And we found our model does not perform nearly as well in Nepal as in Honduras. It's still very useful, but it has some biases in the magnitudes of flow. So we worked with them to develop additional model calibration steps, bias corrections, and to perform some validation studies. And so what we learned from all of this is, I sometimes like to say GeoGLOWS is not just doing science for the sake of science. We're not just concerned about the technical aspects of how do you build a usable model and how do I do the next best data assimilation algorithm and the next best calibration step. We take it one step further and make incremental changes where we ask ourselves, who's the end user that most benefits from a global hydrologic data source? And everything that my fellow presenters have been saying about transparency in model design, reliable access to data, all of those precede adoption. One unique thing that I would add is that GeoGLOWS has also found it's about empowering local people to do this. Every single one of those 4 examples I just listed was principally driven by a local user that came into contact with GeoGLOWS through geo partnerships, or they somehow or another came in contact with one of the researchers that works on GeoGLOWS. And then they took the videos, the training data sets, the GEO Knowledge Hub contents, and were able to make something of it. GeoGLOWS ourselves is not capable of knowing every possible problem and delivering solutions out of the box. So we found it's really in empowering local people. These open knowledge principles is what leads to the success stories that researchers love to share. The collaborative environment is very important. So in the future, we'd love to continue that and see that applied to more use cases. That certainly water is a very important resource that these open practices could benefit. Thank you very much.
Thank you very much, Riley. I really like your focus on users personally. So thanks for the presentation. In the meantime, we have reached the impressive number of 108 participants in this session, which is great. And I also hope to get 108 responses to the next poll question, which will be provided by Florian. So what are the barriers that you still come in your way for knowledge sharing? So please provide your answer in the text field. We will leave that open for the next minute. And once again, I would like to make you aware that you can ask questions in the chat. All right, so while you are still typing, I will continue with the next speaker. Next speaker, I hope I pronounce it correctly, Quillon Harpham. He's a technical director in the Floods Water Management Group and has a PhD in hydroinformatics plus 25 years experience of water sector information systems and data. He has designed, coded, and implemented projects across all stages of the development cycle, including winning a number of awards. He always seeks to provide innovative and sensible solutions. His specializations include data and information management, analysis and design, model and data integration, workflows, marine data, usability, and standardization. He gave already several keynotes and visited several conferences around the world. So please welcome our final speaker for today. Thanks for coming.
Thank you, Markus. Can you hear me okay?
Yes, I can hear you.
Brilliant. Yeah, I might touch on some of these barriers to open knowledge in this presentation. I framed it as a case study, looking at forecasting dengue fever using Earth observation data, and it kind of shows the reach of Earth observation data these days, where we can speak into subjects like dengue fever, which you can't particularly see from satellites. So what I'll do is I'll look at how it works, and some of the issues that we had with managing Earth observation data to do this. So next, please. So dengue fever is one of the World Health Organization's top 10 public health threats. You can see there on the slide the growth of dengue fever over the years. In 1960, there were just 15,000 cases of it recorded every year in just 9 countries, all of them, I think, in South or Southeast Asia. Whereas in 2016, largely driven by climate change, there's almost 400 million cases of it every year in more than 100 countries. And the costs of dengue fever are greater than other major infectious diseases you might have heard of above dengue fever. For example, cholera is just $3 billion US dollars every year to health services, and dengue fever is $8 billion US dollars, mostly in low to middle income countries. So it's a large and growing problem around the world. Next, please. Again, that's right, so that will play. What you can see here is outbreaks on the right of dengue fever. This is Vietnam. Vietnam was the first country that we implemented our DMOS system into. And you can see the rings there circling outbreaks in 2009. So what we're doing is we're cycling through months in 2008 and 2009. And as we get to 2009, you'll see the Vietnam map go red there in the south and the north. Next, please. What you can see there is other factors like rainfall, soil moisture, and temperature in the other 3 panels of that graphic, where what we can do is we can relate outbreaks of dengue fever to changes in these factors. So higher temperature, more dengue fever, higher precipitation, more dengue fever. And the statistical relationships can be quite complicated. Next, please. So what we're doing is we're looking for lots of different stressors of dengue fever, and we're looking to build a history of those and compare them to case numbers of dengue fever. So things like El Nino, for example, even though it's a long way from Vietnam here in the center, El Nino affects dengue fever, and you can track the relationships between the two: a general water availability in the catchments, how land is used and covered, precipitation, temperature, and population. All of these affect dengue fever. But we have to ask ourselves a question: is there enough data? Can we collect enough data about all of these stressors to tell us enough about dengue fever to build a skillful forecasting system? There's Vietnam in the center, divided into its districts and provinces. Can we integrate all the data successfully enough into that spatial structure? And having done so, I mean, we talked a little bit earlier about producing a system that's useful to people. We're not just doing science for its own sake here. And can we produce a forecast that users will understand and apply? And if we can, how are we expecting their behavior to change if we do? Next, please. So what we're trying to do is give users proactive handle on how to control dengue fever. If we can forecast warnings and given warnings in advance, they can take different actions to prevent it happening. And we're trying to either prevent outbreaks happening completely, or we are trying to at least reduce the severity of the outbreaks. And from a week to a couple of months in advance, there's community level actions that they can take to prevent them being bitten by mosquitoes, or to prevent the appearance of mosquitoes altogether. In the medium term, so 2 weeks to a couple of months, district health officers can take action, spraying insecticides, for example, and 5 to 6 months in advance, that's when the budgets get issued. So if you know where your outbreaks are going to happen, you can give budgets to those areas in advance. And we're trying to change the way dengue fever is controlled around the world proactively. Next slide, please. So what we've got here is how the system works. If you look here, you have a history in the past, you have the present, and then you have a forecast in the future. And in the present, we have two models that we run. We have a water availability forecasting model, which is an implementation of VIC and RVIC. And we have the dengue forecasting model, which is a statistical super ensemble model. Next, please. The history we are building into this is a history of a number of different factors, anything from past occurrences of dengue fever to soil moisture, wind direction, population. And you can see here where the Earth observation data is beginning to speak into this. We have temperature and humidity and rainfall, radiation and soil type and stream flow. And we get a lot of this history from Earth observation sources, and we build the history together and map that to occurrences of dengue fever. Next, please. What we do then is put that history into our two models. Some go just into the water availability aspect, and some of it go into the dengue fever aspect, and some into both. Next, please. What we do then is we ingest a forecast, a meteorological forecast of those parameters: temperature, humidity, rainfall, El Nino, and wind speed and direction. And that is from the UK Met Office, and it looks forward 6 months and goes into the water availability model. Next, please. That produces some surface water parameters, which we can also link to dengue fever as a forecast. Next, please. All that lot goes into the dengue fever statistical model, which, next please, produces the probability of an outbreak of dengue fever. Next, please. So this is what the interface looks like. What we have is the probabilities indicated on a map, on a chart, and on a table. And if this were the user interface, you'd click on that little arrow in the mid left, and a movie would run of the next 6 months, giving an indication of where dengue fever is going to occur. And we have these systems in Vietnam, in Sri Lanka, and in Malaysia at the moment. So the forecast is a probabilistic forecast, and different users get different data products as a result. Next, please. So how do we use Earth observation data and manage it in the system? And what are the issues? So firstly, we use a wide variety of free Earth observation data products. So both the more raw products, as well as reanalysis versions like ERA 5. And the whole thing is enabled using Earth observation data products, looking at a history and a live feed of those as well. Next, please. So Most of the systems refresh monthly. They give a new forecast every month, and they give a new forecast each month for the next 6 months. And latency of live Earth observation data isn't an issue in that case. If the systems refresh weekly, sometimes the free live Earth observation data is a bit slow to arrive, but for monthly systems, latency in this use case isn't an issue. Next, please. And again, you know, the great thing about Earth observation data, it gives you your worldwide coverage, and we can do DMOS systems in any country around the world, enabled by the tremendous amount of free Earth observation data we've got in history and in live feed covering the globe. Next, please. It's interesting to note that both hydrometeorological parameters like rainfall and wind speed, and also socioeconomic parameters like land cover and use, all add value to the model. And we're looking for incremental gains all the time in the model, more accuracy coming from hydrometeorological parameters, added to accuracy from the socioeconomic parameters. They all add value, they're all useful, and we're collecting as many as we can. Next, please. Now, considerable post-processing is required to do this. And one issue is that Earth observation expertise is essential to get this working. So there's all these functions that we do against the data. So there's a lot of gap filling and interpolation required. We need to standardize it both to fairly loosely typed international standards like NetCDF, as well as more tightly typed internal standards for the system itself, looking at formats, looking at parameters, and in particular spatiotemporal structures. There's a lot of scaling that goes on to administrative boundaries and weighting to population centers. And all of this requires EO skills and considerable post-processing. Next, please. The workflows create big data volumes. So in the workflow element of the system, as we harvest and post-process all of this data, that creates big data volumes into the terabytes. But the final data products themselves are not big data. They're very small. So the amount of storage we require for all of this EO data only occurs as we're processing it. It doesn't need to be there historically, as the products are very lightweight. Next, please. Now, yes, I mean, this was mentioned before, relationships within country stakeholders have been absolutely essential for success. You know, let me repeat the point that was made earlier. We don't want to do science for its own sake. We want to make sure we want to do useful things, and the in-country relationships have been essential for this process. I think that's my last slide, Markus. Thank you.
Great, thanks a lot for this presentation. Before we come to the final part, we have a final question to all of you in the poll. So Florian, would you please give us the final question? Thank you. So, are you willing to contribute to the creation of the GEO Open Knowledge Guidelines? I will give you a few seconds to answer. All right, so I had an eye on the chat and there were a few questions, but the speakers were also already very busy with answering these questions. So I hope this was done already to your satisfaction. If not, then don't hesitate to raise your hand, and then you can also ask a question here in the session. So are there any further questions from the audience? I would really welcome questions related to the GEO Knowledge Hub, of course. So maybe there are some questions related to that. So I don't see a raised hand or a question in the chat. Maybe I take just the opportunity to ask questions. So I would like to ask the speakers how they see that the GEO Knowledge Hub can reach a more broader community of users. Maybe then in comparison to how research was done before. So some of you mentioned that there is an increased reusability and there's a stronger focus on users and so on. So what do you think about that?
Yeah, I can I would concur with both those points. You can never have too much usability. Things have to be really, really easy to use. Why is the iPhone and the iPad so successful? Because they're so easy to use. You swipe your finger across the screen. And secondly, I would concur with the second point. Let's look to the users, and I think these things occur case study by case study. Let's nail a particular case study and get that working, go on to the next case study and get that working. That for me is the effective way to build the user community, do real things for real people that make an impact in a highly usable way.
Thank you for that. Riley, you raised your hand.
Yeah, thanks. Something that this may not directly answer your question, but something that brought to mind was I think one of the real values of GEO Knowledge Hub is that it is discoverability. At least in my world of hydrology, we're not the only people trying to work on these sorts of needs for water data. But where we've really benefited is initiatives like the GEO Knowledge Hub that make the solutions that researchers work on discoverable to people. Simply not knowing that the data exists is a huge barrier. So we really appreciate any efforts to publicize not just the hydrologic contributions, but everything else that all my fellow presenters talked about today, that the discoverability of models is no trivial barrier to overcome.
Thank you. Robert.
Well, I just wanted to add that I think what the hub also does is force us to think about how to provide all the relevant pieces in one place. I mean, I think we tend to take it for granted that you can do a quick search and find a relevant article in Google Scholar or something, but most users, aren't accustomed to doing that, don't have the time to do it, and so forth. So by creating coherent knowledge packages, I think we really help things, because we can put, tutorials and documentation and metadata and tools all in one place in a more coherent way.
All right, thanks. Any further comments?
Maybe I didn't raise my hand,
Sure.
but we have been discussing in the last meeting of our working group together with a colleague from JRC and from Costa Rica that we actually would need to have more really easy to use workflows, like implemented in sort of web services, that users can say, okay, you find, let's say, your topic, and there is something like you have a question and you can click on some data, or you have like a standard workflow which is step-by-step documented and guides users through this ocean of data, not knowing what, coming from the population model, and also what Bob was referring to. You have so many population data sets out. If you want to know how many people live in place X, it's very confusing for common use, and the same for air pollution, for all kinds of data. So we need to make data more documented and easy accessible, to have summary reports for users on questions they typically have.
Thanks.
Markus, this is Brian. I'll add one other thing. I agree with what Quillon said about having use cases. I really think it's important, if we try to demonstrate this for real outputs and try to engage some users along the way and show the value of bringing all these tools together in one place. So the more opportunities we can get to do that, I know there's a lot of GEO meetings throughout the year. We've got a plenary coming up at the end of the year where we have a lot of side meetings and other things, and a possible exhibition. There's a lot of opportunities there to demonstrate and to work with potential users and get the word out. So maybe that's an option in the future.
Thank you. All right, so I just got a message from Florian that the results are ready. So maybe we can look at that for a few minutes, for 2 or 3 minutes. So we are a bit running out of time, but anyway, let's check. So these are the answers for the first question. So for your activity, what kind of benefits do you see in putting the principles of open knowledge in practice? So these are the answers that you gave. Transparency, inclusiveness is one of them. Access to data, avoiding redundancy is certainly important because data collection is usually very expensive. Knowledge sharing is also in the spirit of the open knowledge statement. We also see open knowledge is very important for the ecosystem accounting, as it promotes transparency and interoperability of data and models. From experience, I can tell that interoperability is certainly one of the most difficult tasks in open science and data sharing. And this also makes it maybe a bit difficult to create easy to use user interfaces, for example. What else do we see? Yeah, one person is saying you increase the likelihood that data are used and help practitioners and decision makers to get the knowledge they need. This is indeed a very important aspect. So we also have to consider reusability. We are not doing open science and open research just for the sake of being open, but we want to make it reusable and get knowledge out of this stuff. Florian, can we take a look at the second question? So what are the barriers that we encounter when it comes to knowledge sharing? Well, time is probably one of the most often mentioned issues, licensing as well, infrastructure, which also costs money at some point, and yeah, several other technical aspects, but also cultural issues that are happening pretty often in research. And our final question: are you willing to contribute to the creation of the GEO Open Knowledge Guidelines? Yes, say 49%, no, say just 6%, and maybe would like to be updated, say 45%. This is a very good number. So considering that we have more than 100 participants, and we can count on at around about 50. Great. So I would like to close the session now. So first of all, thanks also to Paola De Salvo and Florian Franciscakis for organizing this very nice session on open knowledge. Apparently this session reached quite a number of participants, so it is apparently very relevant for many people out there. We saw many very interesting application scenarios for the GEO Knowledge Hub. And as I said at the beginning, if you would like to contribute, get in touch with the GEO Secretary. And yeah, this is just the start. So it's probably the start of a very nice GEO open knowledge era. And yeah, finally, I would like to thank all the speakers for the very nice and interesting presentations. Thanks a lot.